Now we did integer rate decimation and integer rate expansion, and we saw in the very beginning of the module, that is module 2 on multirate, basics of multirate signaling, multirate signal processing, that we are interested in sampling rate conversions, right. We had a studio frequency at 32 kilohertz, and then we want it to be converted to maybe a DAT frequency at say 44.1 or broadcast frequency at 48. We, different sampling rate conversions should be made possible. So the question is, how can we basically do the sampling rate conversions digitally? This is of course the path where we are basically heading towards. So a natural question is, suppose I want a fractional sampling rate conversion, right. I think this is I am downsampling by m. So basically I am reducing my rate 1 upon m and I am expanding it by a factor L. It is, so basically L upon m is my rate, right. So let us imagine the situation that we have x of n at the input. This is upsampled first by a rate L, right, and then we have a filter h of z in the middle. This is followed by a downsampler at a rate m, and then we have the signal y of n. So let us say this interim point is x1n and this interim point is some x2n. So the effective sampling rate conversion is L upon m, right, where we are upsampling by L, reducing by m. So it is basically a ratio L upon m. So let us think about a simple example here. Suppose we have a signal such that x of e j omega, this is the spectrum, is band limited to frequencies less than say 2 pi by 3, 2 pi upon 3. Suppose I decimate by 2, right. If I decimate, if we decimate by 2, this results in aliasing, right, because this 2 pi by 3, right, it will stretch itself to 4 pi upon 3, if we alter the rate by 1.5, right, if you alter the rate by 1.5. So, this 2 pi by 3 point is basically 2 pi by 3 into 3 upon 2, 1.5 is 3 upon 2, and this is basically okay. This goes from minus 2 pi, it basically stretches. So, this is possible. So, this is 2, this is pi here, sorry, this is just pi here, right, 2 gets cancelled and 3 gets cancelled, this is pi. So, this is pi, and of course, minus 2 pi by 3 is mapped to minus pi. So, if we alter the rate by 1.5, this is no aliasing critically. I am saying it is critical because you are touching these points plus minus pi. So, this gives you a sort of an idea how much we can alter the sampling rates such that we do not land up with aliasing errors. Okay. So, you might again question here, what are the approaches for sampling rate conversion? You have a signal, you convert, let us say this is a discrete time signal, you convert it into analog and then you resample at some rate. So, let us assume that let us say we want our rate L upon m to be 1.5, say, just following the previous example, right. So, we want a 1.5 increase in the rate, right. So, a naive approach is take the discrete time signal, convert it into analog signal, right, and then you do resampling at some rate Fs is 1.5 times Fs dash. So, here you have a digital to analog converter and then you need a sampler. It is costly because you need to have hardware for these operations and it is costly. I think a better choice would be do a judicious use of downsampling and upsampling with possibly some filtering in the middle, that is you upsample, you have a filter in the middle and then you downsample, figure out what the parameters of this filter have to be, what your L and M ratios have to be to get you to what you want, to what ratio you want to alter your sampling rate. Okay. So, I think this gives us a basic idea now, right. We get an idea what we really need to accomplish our operations. So, now let us go a little deeper into the filter design aspects and how we can go about designing these filters. suppose h of e j omega is given by this response. This corner point is 2 upon that is the stop band is at minus 2 pi by 3, the pass band is limited here to minus pi by 3 to plus pi by 3, this is the other corner point. And in general we can reduce the sampling rate by any rational number m upon L. I said reduce and I put m upon L. If I said I increase, I would say L upon m. I think that is sort of, it should not confuse you here. Okay. What is really important is the quality of the filter h of z determines the quality of the output. And most of you would have learned from your undergraduate digital signal processing some basics of filters, right. You should have studied Butterworth filters, Chebyshev equiripple filters and so on and so forth, and we can see in this case how we can design one such filter which can give us possibly what we want, right. So, and you can sort of imagine that the stretched versions of the spectrum govern the time domain meaning of L upon m. So, if we were to alter the sampling rate by a factor L upon m, you can imagine that the stretched version of this spectrum, which is x of e j omega L upon m, they govern the time domain meaning of this alteration, right. The 1 over m factor is to account for the decimation, and the factor L appears consistent with upsampling, and you can say that L greater than m is very much possible. Now, let us look at this case here. And we focus on this example. The transition bandwidth is basically 2 pi by 3 minus pi by 3. If you look at the positive side of frequencies, basically this is the same mirror here, right, and between the pass band cutoff is at pi by 3, the stop band frequency is at 2 pi by 3, the transition bandwidth is basically pi by 3, and if you do the normalized transition bandwidth, this is pi upon 3 by 2 pi, which is a sixth. and let us call this parameter normalized transition bandwidth is as delta f. So, delta f is basically 1 upon 6. Belanger, Maurice Belanger, he came up with an interesting formula that connected the filter order with the tolerances on the ripples in the pass band and the stop band for an equiripple filter and the transition bandwidth. So, he was able to connect all of these to suggest the filter order that we need to accomplish this sampling rate conversion process. So, for an equiripple design, so you can imagine the response would be something like this. Right, I did not do mod h e j omega, I just did h e j omega. So, therefore, I have this magnitude, then you will have to really. So, basically these ripples could swing between minus delta 2 to plus delta 2. This is your pass band, this is your stop band, and in this, let us say the nominal gain was 1, and I could have a 1 plus delta 1 here and a 1 minus delta 1 at this point. Okay. Now, somewhere it is pi. So, n, he came up with this formula which is basically an empirical result. This is 2 log to base 10 of 1 upon 10 delta 1 delta 2 divided by 3 times delta f. So, delta f, this is the normalized transition bandwidth, and delta 1 and delta 2 are the tolerances for this equiripple filter. If it is Butterworth, it is pretty much flat, right. If it is equiripple, you are basically having these ripples in the pass band and the stop band. So, now suppose delta 1 equals delta 2 is a 0.01 for an equiripple filter, right, and delta f per our calculations in the previous slide, it is basically 1 over 6, 1 upon 6, right. This is what we said, this is what we ideally want. Ideally we would want it like this, but it is not possible, but we say we will tolerate some ripples in the pass band and the stop band. We have a normalized transition bandwidth of 1/6. So, you plug into this formula, you will end up with n to be approximately 11, that is we need a 11th order filter. And the details of as to how we can design, I mean we have equations to get the filter coefficients. If we can pull up a manual for the design of such filters, right, and then we can basically go through the exercise of computing the coefficients of the filter, and we get an order, and once we know the order, depending upon the governing polynomial and the equations to get the filter coefficients, we can just extract the coefficients out, and that will give us the design, right. So, this sort of gives you an idea as to what is desired, right. So, basically I want a sampling rate conversion to happen, and in the process of getting the sampling rate conversion I have to ensure that I also have this filter that I need that has to work with, because ideally brick wall filters are not possible. I mean the order is really infinite. If you have to realize ideal low pass filters, you are not going to get that. So, basically we have to approximate the brick wall filter by an approximation, right. We need some kind of low pass filter with a practical order that we can implement. To get that, we should know what the pass band is, what the stop band is, and these are the details, and once we get those details we can basically figure out where we need to build this